The second thing I want to talk about has to do with doing integrals, and in particular finding arc length or surface area or doing a change of variables. Each of those had these distortion factors that we had to multiply by to get the right answer. One of them was speed when we were calculating arc length. One of them was this cross product length of these two tangent vectors when we were calculating surface area, or when we were doing the change of variables, we had this Jacobian determinant factor we multiply by the absolute value of the determinant of the Jacobian matrix. And there's some kind of common theme running through these formulas, but they look very, very different. And so the problem with this is that these formulas are really useful. They're straightforward to calculate. That's why we give them to you in this class, because they're the most effective means for calculating the answers, but they also don't look great. And they are wildly different. And because all of these are doing the same kind of thing, we're all measuring the total arc length of something, the total surface area of something, the total volume of something, we think that there should be some kind of pattern going on behind the scenes that unifies all three of these. And there's a unified formula that works for all three of these. So suppose we have a shape and it's parameterized by some function capital F. So capital F could be a curve depending on time, or it could be a function of phi depending on a surface, or it could be some kind of three variable change of variables type description. We write down its Jacobian matrix, df. Now, df is probably not a square matrix, but here's what we do. We take df transpose, where we flip this matrix across its diagonal. We multiply it by df in this order. That result is now going to be square. We take its determinant, and then we take the square root. That is a unified formula that always gives us the correct distortion factor. So for example, if we're parameterizing a curve, the matrix df is just the tangent vector c prime. We multiply it by c prime of t transpose. That's the same thing as the dot product. When we take the determinant, this is a 1-by-1 matrix, and it just gives us the number back. And so we're just taking the square root of c prime of t times c prime of t. But this always gives us a formula that has the right answer. If you feed in a Jacobian matrix for a change of variables, it always gives you just the absolute value of the determinant. So this is very handy, and it has important consequences geometrically as well.